My name is Jimmy. It's thanks for being here with us today. It's a great honor to present our recent work at ICCV 2021, the RealWorld Accessibility, Vision, and Autonomy Meet. Before we get into that, let me give a brief introduction about myself and the team. I'm the second-year PhD student working with Professor Ashad Anbar, and I'm interested in computer vision, machine learning, and robotics with their applications in autonomous, assistive, and accessible systems. And we also have Minglan here. She is a senior in computer science major. She will talk about our RealWorld platform designing and how we use that to set up our benchmark. So let's get into that. So an important issue facing the vision-based autonomous system is the lack of accessibility-aware development, which leads to increased risk of traffic fatalities for the people with disabilities. For example, the Starship technology, it is a company who developed this delivery robot. It paused its operation after only a few days after its deployment at the University of Pittsburgh in 2019, because its robot routinely occupied the curbs ramp while waiting at the intersection. It blocks a disabled doctor student from boarding the sidewalk safely. As a result, the student had to wait at the intersection among all those moving traffic. It's quite dangerous. And another recent case involves Toyota suspending the use of its self-driving bus after colliding with visually impaired athletes at the Tokyo Paralympic Games. And the case is when the bus turned into the crosswalk, it collided and hit this visually impaired athlete. And so they suspend this service. So we can see that both of those cases are quite unfortunate. People with different abilities may react quite differently with autonomous platform and the dynamic context of the environment and even the infrastructure components. So obviously, when those prototypical autonomous systems move from their controlled development lab into the real world, they fail to consider their impacts on the people with disabilities. So in our research, the key question is, how can we realize a system that seamlessly interacts with all people in their environments? So a fundamental barrier to realize such a system is the access to the data. In particular, people with disabilities are quite diverse in their appearance and mobility characteristics. And also they are quite rare. For example, like the disabled people are currently entirely absent in the large-scale data sets such as Cityscape, Coco, and Kitty. So in our work, we took an important step forwards towards developing such perception model that can be both functional and robust in dealing with such scenarios. And we call our tool RealWorld. And in the next part, Minglan is going to talk about the detail about our RealWorld solutions.
Oh, thank you, Jimmy. So so to solve this problem, we developed the RealWorld platform, which I will describe in the next few slides. So in building our accessibility-centered world, we thought to leverage the recent advances in simulation rendering, in particular Carla, which is an open source software implemented in Unreal Engine. While Carla has a rich array of environmental conditions and digital assets, it does not provide any support for accessibility-related event. So we introduced a photo and behavior realistic module into Carla that can spawn agents which uses various mobility aids and extensive ground truth generation for different visual semantic task reasoning. So on the next slide, I'm going to show a clip of driving in our accessibility center simulation world. Overall, we include 28 models of wheelchairs and canes that can be attached to any existing pedestrians in Carla. So while we focus on this two type of mobility aids, additional mobility aid models can be integrated in the future. To model realistic pedestrian appearance and dynamics, we manually set kinematic parameters, including gates and damping factors, and incorporated canes and wheelchair techniques to match real-world behavior. So we now use the simulation to analyze an instance segmentation task in the context of the urban scenarios. And to obtain the instance segmentation mask, we back project the semantic segmentation map into the 3D point cloud and use the 3D bounding box annotation to determine a instance ID per pixel. And this gives us pretty accurate result as visualized on this slide. Then we collected data across 6 camera perspectives, 5 towns, 6 ambient settings, including different weathers and times of the day, our novel pedestrian type, and the extensive set of mobility aids. Our final simulation data set consists of 72,000 images sampled from 40 hours of videos driving in the simulation. Along with the simulation benchmark, we also include a small but diverse real-world benchmark for validating our results more comprehensively. So because collecting a representative real-world benchmark is difficult due to the rarity of encounters with pedestrians with disabilities, so we leverage Institute navigation videos and images from publicly available internet sources. Overall, we select 80 videos, and then we deliberately select a subset from the images to ensure a meaningful evaluation and model generalization. And the subset we select involve dense urban traffic and a variety of pedestrian poses, camera perspectives, and geographical location. Before we dive into the experimental analysis, we're going to first look at the statistics of the 2 introduced benchmarks. So we're now looking at the density of categories and instances per image. When compared with other public dataset, our simulation dataset, which is the purple line drawn, it has more complex images with crowded pedestrian and vehicle, as the tail is a bit longer. And these 2 figures provide a breakdown for per category pixel statistics and pedestrian size statistics. So note when comparing with existing benchmarks such as COCO and Cityscapes, our simulation benchmark, which is in purple, has a similar distribution as Cityscape because they're both collected on road settings. And also Cityscapes and COCO do not have the annotations for wheelchair and cane. Another observation we made is that our simulation benchmark, while we try to collect as many near crash events as possible, it has this tendency to have larger, smaller size images, smaller size instances that are further away from the camera. This is kind of to be expected because when you're in a traffic intersection, there are like pedestrian and vehicles that's in the background. While in contrast, the real world benchmark from the publicly internet sources tend to have this bias of larger objects that are closer to the camera. So I'm going to now pass to Jimmy to talk about the experiment and findings.
Where is my first slide? Where's my first slide? One of the. So there's something wrong with our slide. So as you can see, we skip directly to table 2. Table 1 is missing. So I will try to show. Do you have the paper here? We can maybe show the paper here. No. Yeah, the poster. Okay. Ah, this is too small. Okay, so we'll just use our paper here to show the table 1. Sorry about that. All right, cool. So we begin our experiment by evaluating the traditional person detector. And the common approaches only have the singular person category. And they are agnostic to a different type of person, like the wheelchair person or the visually impaired person. So, but while they are not supervised to recognizing such person type, we can still leverage our annotations to uncover their performance in our testing. So we provide a breakdown through all those introduced person category. And as we can see, the off-the-shelf Mask-Garcia model cannot handle the introduced wheelchair person category. If we look at the first and the third row here, they achieve pretty low performance on wheelchair person. And after fine-tuning such model on our data sets, we can see that we can still see like a reduced performance on the wheelchair person and the visually impaired person. So that's it for this. Let me just go back to our. There another one. It's the old version. This is the old version. This is the old version. It's not this one.
What's this one?
A second. Open. All right. So in our next experiment, we introduced more accessibility related categories, including the wheelchair person, visually impaired person, the rider, 4-wheel vehicle, 2-wheel vehicle, wheelchair, and can. And we test them under harsh generalization settings of new town, new weather, and previously unseen new mobility aids. And as we can see that we surprisingly find that even trained with the ample training data, the model still cannot handle those introduced mobility aids. As we can see, it's fell on the can category, and it also like the wheelchair category is always like misclassified as the 2-wheel vehicle. We'll show more examples in our qualitative results later. And also, when considering those 4 generalization settings, we find that usually it's hard, testing under the new mobility is harder than testing under new weather. And we follow the recent no crash benchmark to split our training and the testing weathers. And obviously those testing weather, new weather is not that challenging for our novel task. But we can easily generate some more difficult benchmark by introducing more drastic weather conditions and the different appearance, pose variants, and so on. So we still reiterate our findings of novel challenges introduced by our RealWorld platform and the benchmark. Yeah, sure.
So I'm guessing the rider here is like bicycle.
Yes. The bike or the motorcycle. Yeah. So in the end, we utilize our real-world benchmark data sets and to do this final real-world benchmark analysis. And we find our result on the real-world benchmark to be generally consistent with our result on the simulated data sets. As we can see, it cannot handle the wheelchair person very well. But one difference is the visually impaired person, the performance on the visually impaired person outperforms the non-disabled person. We think it's because in the real world data, it's like the image contains the large, isolated, centralized visually impaired person, which provides the easier settings for the segmentation and detection task. And to further validate our simulated data sets, we use our real world image and try to analyze the simulation to real generalization. And as we can see, if we use the model trained on the simulated data only and test it on the real world data directly, it failed because of the large domain shift. But we still want to utilize our simulated data sets to boost the performance on the real world data. So we combine the simulation data set with our real world training sets. And as we can see, by combining those 2 data sets, we see improved performance on the mobility aids, the wheelchair and the can. And also the simulation data set helps segmenting those wheelchair person. And in the end, I want to show some qualitative results. Here are some successful cases. As we can see, using our RealWorld platform, we can detect and segment those 8 accessibility-related categories well in those cases. But we also have some like failure case. For example, in the first image here, the rider is misclassified as the visually impaired pedestrian here, and also those, for example, here the visually impaired pedestrian is misclassified as a rider. So those 2 classes are quite confusing. And also you can see here the wheelchair is misclassified as the 2-wheel vehicle. And also as we can see, the can is very hard to segment due to its geometric shape. Sometimes because it's too tiny, we cannot even detect them. If we look at the simulation image here, there's the visually impaired pedestrian over there, and it didn't. We cannot detect its can because it's too thin, and also due to the occlusion, sometimes segmenting the wheelchair can be extremely hard because a large portion of them is blocked by the visually impaired person. So in summary, we introduced the interactive environment for learning robust models for machine perception of diverse people. And this introduced the accessibility-related instance segmentation task, introduced novel challenges complementary to the existing benchmarks. Thanks. Any questions?
All right, thank you for a great presentation. Now I think we can take questions. Does anyone have questions? Yeah, well, I'm going to try use the microphone for the sake of recording.
So for your test set, do you have like a breakdown for the number of different samples for each category that you're trying to predict, and like how sort of frequent you have, like what's the frequency of like people with wheelchair in the test set as like real data set?
So you mean how many wheelchair person in the testing set?
Yeah, and
yeah, we do have that.
It's like also the real one, that not the simulated ones.
For the real one, do we have the statistic for the real one? Yeah, we do have the statistics for the real world testing sets.
So for the real world, we have 1,400 pedestrians, including 264 in wheelchair and 209 cane users. And for the simulation, it's the statistics.
Sure, and do you know if like the sort of diversity in sort of pose and situation that the sort of wheelchair sort of image test set compared to like actually like the people, the normal person sort of samples, right? Are you sure that sort of your test set can be inclusive enough to all the possible sort of diversity in pose and situations and all that wheelchair people can exist in, right?
In the real world?
Yeah.
So currently, it's really hard to collect the real world scenario, especially let alone like we want to collect those wheelchair disabled people. So what we do is we use the online resources. We try to cover as like diverse as possible, but it's still impossible to cover all the scenarios, all the situations. But this project is still ongoing. We're collecting more data from the online. So in the future, we will have more diverse and try to cover all these.
Okay, and so one last thing, since you're trying to expand this to be more inclusive and all that, did you try to like sort of reach out and like have researchers or people sort of that come from these backgrounds involved in like the data collection and involved in like having their opinions be like,
sorry, I don't understand your
so since you're trying to sort of make this method more inclusive toward people who are just not persons, right? In your data collection pipeline and you're engineering your methods and all of that, did you try to have like sort of opinions for people from these backgrounds, like sort of delve in and tell you what they think of expanding these models?
Yes, we have an ongoing user study with the like a what's the center called? The Carroll Center for the Disabled People, and we conduct a user study, like try to navigate them from the indoor scenario to their Uber, and also try to navigate them in the urban scenarios. At the same time, we collect the data from a third person perspective. And after those user study, we get the feedbacks from them. How do they think about our surveys here? And how do they feel what's the most comfortable way to navigate them in the complex urban scenario? So we do have such user studies.
Sure. Sure.
Thank you.
Any more questions?
Hi,
Hello.
this is really cool work. I was wondering, how did you designed the like movement dynamics? It sounded like they were manually engineered. Yeah, I'd be curious.
So because Carla is implemented in Unreal Engine, so we basically use the modules that's in Unreal Engine to use animation that's transformed from motion capture, and then apply the animation on the existing pedestrian that's in Carla. And then we manually twin some kinematic parameter to make them fit to the behavior of a disabled pedestrian.
Did you have like these videos also looked at by people that use wheelchairs, or like people that assist those with wheelchair use or canes?
Yeah, we currently do not have people like with those things, but it's definitely one of the things we want to improve in the future because we want to make it more realistic. So we checked some of the paper they're studying these the kinetics of those disabled people, and we will in the future incorporate that into our export platform. Okay.
Cool.
Hi, thank you for the presentation. Did you consider including maybe like service dogs or people with crutches or walkers into the data set?
Definitely, because we actually, when we try to develop this export platform, we do consider include those service dogs, and but it will kind of make our task more challenging because we cannot tell the difference between the service dog or other dogs, and also the like visually impaired person with the people just walking the dog. So that's why, and also like currently we do not find, like previously we do not find a model for the service dogs, but we will definitely include that in the future. It's a very good idea, and will make our platform more realistic.
Thank you.
Okay, any more questions?
Great. So again, thank you. I really like this work. I guess the thing I'm kind of curious. There's a few things I'm kind of curious about. One of them is, do you think that a lot of the confusion you have, let's say, between categories is maybe the imbalance or the lack of data in particular when we're looking at, let's say, the riders versus the people with canes? It seems like these, occur a lot less frequently. And do you think if you, try to balance out the data set, the model would be able to better identify these categories?
You mean balance the category for example, like make the rider and the
Yeah, and same with like the regular pedestrians to have all of them be more balanced.
We do not do that like in the training because we want to. So one thing is in the real world, those people that like disabled people are quite rare. So we do not need to like manually introduce the more visually impaired pedestrian or the wheelchair pedestrian in our test. We want to make it realistic to the real world image, but during the training for this task we didn't try those tricks to balance those different samples or hard samples. But so for this task we only want to review that how challenging this task can be, and we only tried the NASCAR CAN and the traditional way to train those model, and to see if we train the model in the traditional way, it will fail. But we can definitely train some. We can definitely use some tricks to balance those different samples, and also even try to. We are currently trying some sim-to-real generalization models on our set. So we want to see like if the current the state-of-the-art method could help solve this problem. Yeah, so we are trying that. For this task, we just want to review the difficulty of this problem.
Okay, great. I guess another question is that, so you kind of motivated this as a maybe an aid for autonomous vehicles or something along these lines. But it looks like you're trying to subsample this, so that you're basically making these predictions based off just images. But if you were working with an autonomous vehicle, you'd basically have video information. And I guess one of the key things that I would think are missing there are the speed of the different users.
So if you look at our platform, we do not only have the image, we also have the image, we have from the export platform, we have the semantic segmentation camera, we have the depth camera, we also have the LiDAR, and we also have like other way to collect those like CAN information of the vehicles from our export platform. So if you want to use other sensors in your methods, the export could provide us like almost all the sensors you can come up with right now. Like currently, all those autonomous driving companies are using. So yeah.
Okay, great. And I guess the last one is kind of a bit more of a hypothetical. So some of the challenges, let's say with canes, as you said, are because they're a little bit too thin, so they're hard to see. But it seems like that usually someone who's using a cane has a relatively particular body pose that might be uncommon for other users. Have you thought about using, let's say, like human pose estimation to improve the performance of the model? So I'm asking you, have you thought about it? Do you think a human pose estimation system would be useful for this task?
So we're currently Meanline is working on a human pose benchmark using our export platform. So and similarly, we have a mesh. We try to detect the mesh of those pedestrians on all the obstacles. So they are all related to the pose of those disabled people, and we'll see what we'll find in that benchmark.
Okay, great. Yeah, thank you.
Okay, any more questions? All right, then let's, okay, one more question.
In the tables, I've seen that after the addition of the extra data, your performance on regular persons also improved, right? Am I reading that correct?
So you mean one of our tables?
Yeah.
But by the way, so we use non-disabled person as the term. We don't want to cause like a normal person because they are not normal. So cause non-disabled person.
Okay, thank you. So I'm reading this after, in the second line in each block, person is increases from 30 to 62, for instance, in the first table.
Okay, so first table.
Person?
Yeah, person. So you mean the non-disabled person also?
Yeah.
Because in the first line there, we use the off-the-shelf model to test on the simulation data set directly.
Oh, I see. I see. Okay. All right. I was just thinking maybe addition of this variation in the data may also increase the robustness. Yeah, but yeah.
All right, then let's thank our speakers again for the wonderful presentation.